Okay, let's switch to English. Welcome to our next lecture in P2P Systems. Here we have two topics. First of all, I want to tell something about the security risks and the issues and problems in P2P systems. And the other topic is the BitTorrent, but I don't think that we get this far today. Okay. So the first topic is about the attacks and its countermeasurements. Every peer-to-peer system we talked about has an additional shortcoming. It is the lack of security. Okay, first of all, we have these DHT components. We have an key identifier space and node identifier space. We have rules for associating keys to nodes, per node routing tables that refer to other nodes, and rules for updating routing tables as nodes join and leave. And any of the above mentioned may be a target for the attack. So for example, a malicious node in code can deny object requests for which it is responsible for. Another attack may distort the routing, for example, by forwarding messages to wrong nodes. Thus, the message may be forwarded in a cycle. Okay, now we want to discuss the attacker model, which explains how corrupt nodes may behave. In the literature, there exists three categories. First of all, nodes that do not follow protocol correctly. These nodes have no evil intention, so it may use a faulty implementation, for example. The other category are nodes that follow a protocol that benefits them. So these nodes want to have less costs, so the traffic, for example, but want to get the best quality. For example, in Kademlia, a node may state it is transients to avoid other nodes add it to their routing table. And the last category are nodes that follow a protocol which is harmful for the network. These nodes are called malicious nodes, and they may spend more power to harm the network, for example, to disturb or even shut down the routing in the network. So what are the assumptions for malicious behavior? First of all, malicious nodes can generate arbitrary packets, which also includes forged source IP address. But the node cannot receive packets addressed to other nodes. So a node can only receive packets addressed to itself. Okay, and also malicious nodes can conspire together, so they build up a collusion, and they can do the things we just talked about. So these are cooperated malicious nodes, and they are very dangerous because they have, for example, more possibilities to shut down the routing. Imagine a routing process in CORD where one malicious node sent a message to its cooperated node. This will result in a routing loop as all intermediate nodes forward the request, for example, deterministically. So we talked about the possibilities of an attacker, and now we want to look at how to cause harm on different layers. First of all, let's have a look at the application layer. So, for example, malicious nodes may give false responses. For example, they may pretend to be unreliable and weak in terms of bandwidth and computation power. Also, they could use free writing. For example, in file sharing applications, one can simply delete or move finished downloads to not contribute on sharing this file. Okay, so how can we fight these attacks? The first countermeasure is to rewards for good and penalties for bad behavior. For example, BitTorrent uses this. This is called tit for tat. And we will address this on our next topic. The appeal is something like give more to get more. Okay, let's proceed to the network layer. We saw how nodes can perform attacks on the application layer, for example, by telling wrong capacities, for example, the bandwidth, or by not contributing. Here, malicious nodes may modify the protocol in order to harm other nodes in the network by providing false information about the network state. Also, we could have invalid lookups. So messages are forwarded to invalid, non-existing or random nodes instead of the correct ones. Or they even can drop the message. This is a waste of bandwidth, time. Okay. Also, another attack is concerning the invalidity of routing. So the corruption of routing tables can lead to bad behavior. So malicious nodes tell false information in order to disturb the routing process. So honest nodes are used to unconsciously forward messages to wrong nodes. And then we have the attack type of partitioning. This is the king class of malicious nodes objectives. Here the bootstrap to a malicious node could lead to the node being kept in a second network consisting of only malicious nodes. Yes, for example, this can be achieved if a malicious node is used for this bootstrap, and this node is controlling the whole second overlay, which is populated by malicious nodes. Okay, now let's talk about a class of attacks, the identity-based attacks. The goal of the attacker is to take over a desired place in the DHT. This is done to gain a benefit. So the attacker gets the responsibility of an object ID, and then he can, or it can do whatever it likes. So, for example, deleting this object or modifying. And also, it could use the benefit could be to cut off a node. Okay, it is. Okay, which requirements do we have for the solution? So it's very important that a node cannot freely choose its node ID. Otherwise, those attacks are a piece of cake, and node can gain the responsibility of every object it likes. So ideally, every node should be placed at a completely random place in the overlay. Also, the verification of node ID is important. To be sure that the sender of a message is really the one who is pretending it. For example, a node may fake a message and send "I go offline," and then this node will be kicked. And the routing tables of the neighboring nodes will be updated. Okay. Here I want to present an identity-based attack called the Sybil attack. This attack is only possible if an overlay allows to choose the node ID freely. Okay, this Sybil is the title of a book about a schizophrenic woman. She's called Sybil, and I think she had seven different identities. Okay, the Sybil attack. The idea of this is that a single node joins the network with multiple identities. So we have one physical entity, and this possesses multiple logical identities. The result is that an undermining of replication, which leads to data loss and fragmentation, so this leads to data leakage. So like mentioned in the last lecture, in past, for example, a Sybil attacker could place some identities around an ID it wants to own, and all its replica will be taken. So this node is able to remove an object completely with its replica. Another result is that the entities gets more global view of the network. Thus it can plan when and how to attack the overlay. The observation of other nodes is also possible if the logical identities are placed in the right positions. And we have also a lower robustness. So if this one physical entity fails, all other logical identities will also fail. So this may lead to a partitioning of the overlay, depending on the structure of the overlay. Okay, here we have an example in Cademia with 4-bit identifiers with 4 Sybil identities, which are marked red here. So in this case, the attacker controls 25% of the network overlay. Okay, this network is not quite big, but on failing, the stabilization of this overlay may also take a while. So we can further intensify attacks, as this attack type is not very critically and often combined with other attack types to cause more harm. So here we have another method to cause harm in the network. It's called the eclipse attack. Here some nodes get together to manipulate a node's routing table, thus eclipsing this node. Even parts of the network can be eclipsed, so honest nodes are prevented from contacting each other. Also, the eclipse of parts of the network can enable censorship. So also a Sybil attack can be used to perform an eclipse attack. For example, by positioning the Sybil nodes around the target. So the Sybil attack is not necessary. Even if we have some countermeasurements against a Sybil attack, an eclipse attack is still possible. For example, the Eclipse attack can be performed by a group of malicious nodes or maybe botnets. Okay, also a requirement for an Eclipse attack is the free choice of node IDs. Okay, here we have a small example with Academia again, and again with 4-bit identifiers and 4 Sybil identities. So in this example, the Sybil identities control an ID or all IDs starting with 11 and can therefore delete or modify these objects. Another example, so not Academia, imagine a CAN overlay. If we perform an Eclipse attack there and position our identities in a circle, we will be able to divide this overlay into 2 parts. So we have the inner cycle, our malicious nodes, and the outer cycle in this CAN network. By doing this, the malicious nodes are able to control almost every communication. Thus, they can enable censorship. Okay, now let's find solutions against identity attacks. First of all, it is required that we have a verifiable ID, and the ID generation should be limited, so we should avoid free picking. Here we have some suggestions how to reach this. So we have something like pay for your ID, and first of all you can pay money to get an ID, but this approach was not accepted as no one would pay money to get an ID for an overlay. And the other suggestion is to pay with computational time. So the user has to pay with its time. Yeah, this should hinder malicious nodes from quickly creating multiple instances to join this overlay. So there exists some approaches to realize this. We will come back to this later with crypto puzzles. First of all, I want to present the secure ID through trusted third party. Yes, this is an approach how to limit Sybil and Eclipse attacks with ID signing methods. So let's assume a trusted third party which controls the node ID assignment. This is, for example, something like an overlay provider. So where a potential user can request an ID and the trusted third party provider assigns this ID to a node. Okay, this is often combined with a reputation approach. So all nodes report observed misbehavior to this trusted party, and this trusted party analyzes this behavior, so they check this report, and then they can revoke this node ID of this malicious node. We have a lot of shortcomings here. For example, as central instance in a peer-to-peer, this is not a good idea because there does not exist a third party which is trusted by every node in this overlay. So this approach is not accepted by the peer-to-peer community. The approach, here we have another approach how to deal with Sybil and Eclipse attacks. And this is, how can we verify our ID? Here's an idea to verify our ID through a device bounding. So yes, we bind our node ID to device characteristics. For example, this could be, so our node ID could be the hash of our IP address, our port, maybe the MAC address, and the round trip time between a node which is randomly selected from the same subnetwork. So the node ID is partly fixed because there are some limitations. For example, the port range is fixed, so we have 65,000 and some ports only. The IP is also fixed because nodes want to contact you, and if you fake your IP, they won't contact you at all. So this makes a free choice of ID very hard, and yeah, as also a hash function is used on this device characteristics. We have one shortcoming here. The node ID changes if a user logs in from another computer, because the IP port, etc., the MAC address will change. But ideally, the node ID does not change to not lose potential collected reputation points. For example, in a file sharing application where you get reputation points whenever you contribute to the network. Here we have another approach. This approach, the generation of IDs in this approach is deterministically. So a node keeps its ID. This is called ID-based cryptography. This approach is also used by web peer-to-peer, which I introduced in the last but one lecture. So I go through this very quickly. Yes, we have the identity-based cryptography, so we use the asymmetric public key as our node ID. And the goal is that we can verify our ID and establish secure communication. Okay, here we have an example of this. Here we have a chord ring with some nodes, and those nodes use their node ID as the public key, and so they can communicate encrypted. So the direct communication is encrypted, and the routing messages are also encrypted, but they are hop-to-hop encrypted. Also, we can use a signature here, so we can verify it. Okay. Yes, this allows for instant encrypted communication, as I said, and the verifiable content with a signature, which the sender appends to the message, and the receiver can check this signature using this node ID. So a node ID cannot really choose its node ID, because otherwise it could not decrypt received messages or signed messages, as it needs the corresponding private key. As you might know, the generation of the private key out of the public key is not possible in asymmetric crypto algorithms like RSA or ICC. And also we can use, okay, so first of all, the node ID will be quite big if we use RSA public keys. For example, we have a node ID which has 2048 bits. With this also the routing tables grow. So instead of using RSA, we can use, for example, ECC, which is the elliptic curve cryptography. Here we get an equally security level with much smaller IDs. So for example, in the web peer-to-peer we use IDs that are 256 bits long. Okay, here we have also some drawbacks. First of all, we have a more traffic overhead as we have larger messages because of the encryption. Also, we have a calculation overhead as every message is encrypted and signed, which is not very performant. But nowadays, it's not a big deal because computational power gets better. Okay. Here we have an Eclipse attack where the attack can partition a network. This attack type I already mentioned, so I go fast through this slide. Okay, so if the new node contact an attacker first, the attacker can partition the network. So yes, so the attacker can even hijack nodes from the real network. The parallel network is consistent for the honest node, and it looks okay for him because there's, for example, we have something like this is our chord ring. We have here some nodes, and this node is, for example, a malicious one. So now a new contact wants to join this node, this overlay, and it contacts, for example, this malicious node. This malicious node could say, okay, here we have a chord ring, and you can join this chord ring. So this node is also here, and he say, okay, join this overlay. This overlay, there are currently only you and me, and for the node, for the honest node, this seems okay. So this is the idea. Okay, how can we? What is the solution for this? We could use Bootstrap from a trusted source, for example, but this is quite hard because it's hard to get it in a dynamic network. But public keys might help here. Another solution is to cross-check routing tables with random queries. Yes, so this assumes we were part of the network earlier, but still totally safe. So this is kind of unlikely in a partitioned network, as the users in one overlay do not know anything about the other overlay. But this can be used to discover other Eclipse attacks than the partition attack. We will come back to this later. Okay. Okay, in the 10 minutes I can do the crypto puzzles. Okay, here we want to address another approach, how to counter the Eclipse and Sybil attacks by using computation power to generate the node IDs. Yes, first of all, a motivation for crypto puzzles. Yes, the payment with real money is difficult to handle without a central authority. The central authority in a peer-to-peer network is not good, and so nodes can pay with their resources instead. So with their storage, bandwidth, and computing power. Okay, for example, the generation of a node ID can take 3 minutes, so fatal Sybil attacks are practically impossible. There are 2 types of crypto puzzles which we want to study here. First of all, we have this static crypto puzzles. So the ID is assigned, so we cannot choose the ID, and it is very time consuming calculating the node IDs here. Also, we have the dynamic crypto puzzles. Here, the ID may be chosen, but it is still consuming, time consuming, sorry. So this is maybe for Sybil attacks, and the static crypto puzzles is for Eclipse attacks. Okay, we have some assumptions here. Yes, the computing power rises over time, as you know. So computations that take a long time now will perform faster in the future. And we will have some constants on the next slide, and these constants are the costs for generating the node ID. So this is the main idea. Okay, let's come to the crypto puzzles and how the algorithm works. On the left side, we have the static crypto puzzle, and on the right side, we have the dynamic crypto puzzle. So first of all, we generate a key pair, as for example an RSA key pair or ICC key pair. Then we calculate the hash of the public key. This is our P. And then we check whether this P has C1, so this is the constant, C1 preceding bits which are 0. So if this, if the answer is yes, our node ID is assigned as the hash over the public key. Otherwise, we generate a new key pair and try this again with this key pair. So recalculate the hash of the public key, and again check the preceding C1 bits, whether they are 0. So if C1 is big enough, it could take a lot of time to generate this node ID. Also, the ID check is very easy to handle here, because we can simply take the node ID, hash it, and check whether the preceding C1 bits are 0. Okay, and we have the dynamic crypto puzzles. First of all, generally, this is another approach. The node ID can be chosen freely, but another ID, which is called X here, has to be generated to fulfill some requirements. So let's jump to the algorithm. First of all, we calculate the node ID of the hash of the public key. Now we choose a random number X or ID X. Then we calculate the XOR of node ID and X and hash this. This is called the P. And here again we check whether the preceding C2 bits in P are 0. Yes, if we fulfill this requirement, the dynamic crypto puzzle is solved, and we can set the node ID as our the hash of our public key, which we generated. Okay. Yes, both approaches take a lot of time to calculate a valid node ID. In the static approach, the node ID cannot be chosen freely. In the dynamic, the node ID can be chosen freely, more or less. Okay. We don't have more time, I think. Yes. Okay, so the next lecture, which will be held by Professor Graffi, is about routing attacks. And yes, securing routing attacks and attacks on the storage retrieval process, and also how to realize an access control on our objects. And also we have this BitTorrent application. Okay, so do you have any questions regarding these topics? Okay, then we are finished, and thank you for your attention.